Hello, this is Nirmal Ganguly. We are going to start the course on electromagnetism. So, before starting the topics of electromagnetism, that is electrostatics, magnetostatics and electrodynamics, some part of electrodynamics, we would rather like to brush up our vector algebra and vector calculus. Maybe many of you didn't study vector calculus earlier, although you have studied vector algebra. It could be a good idea to go through vector algebra and vector calculus once more at the beginning of this course. If you are confident about these topics, you may skip this part and go to the next part, but I recommend going through this part once again. So, let's start with vector algebra. In vector algebra, we first briefly mention addition of two vectors. So, if we add two vectors, vector A plus vector B, that's commutative. That means we get vector B plus vector A. These two are same things. It's also associative, meaning A plus B. If we now add another vector C to it, that gives us the same thing as this. And you are familiar with some of the vector products. The first kind of product is multiplication by a scalar. Here, small a is a scalar and we are multiplying the sum of two vectors A plus B with this small a. This just gives us small a times A vector plus small a times B vector. Now comes product of two vectors. One type of product is called dot product. Here A dot B, this quantity is given as A B cosine of the angle between the vectors. Say this vector, say this vector is A, this vector is B, and the angle between them is theta, then the dot product is given as AB times cosine of the angle between these two vectors. This dot product is also commutative. That means A dot B equals B dot A. And it's distributive. That means A dot B plus C equals A dot B plus A dot C. Let's see an example. Let's consider a vector C that's given by A minus B, and we want to calculate the dot product of C with itself. That means we are interested in calculating C dot C. How do we do that? Let's draw these vectors A and B. This is vector A, this is vector B. So, C dot C can be written as in the algebraic form A minus B dotted with the same thing, that is A minus B. This is given as A dot A minus A dot B minus B dot A plus B dot B. Which means because of its commutative property, we can write have A dot B equals B dot A, and that gives us A squared plus B squared minus twice A B cosine of the angle theta between the vectors A and B. So, this quantity can also be expressed as C squared. This is known as the law of cosine. Okay. Now, let us move on to another type of product. So, with dot product between two vectors, we got a scalar. Here, we will now deal with cross product. Cross product for two vectors gives us a vector quantity, and the cross product is defined in the following way: A cross B is given as A B sine of the angle in between and n cap vector, which is a unit vector along the perpendicular direction to A and B. So, if this is A vector and this is B vector, then the angle between them is theta, and A cross B would be AB sin theta is the magnitude, and the direction would be perpendicular to both A and B, that is perpendicular to the plane of this screen, but it is important to know whether it would point outward or inward to this plane. So, the idea is that we will apply the right hand rule. We will align the fingers except the thumb to A vector first and then rotate it to B vector. In doing so, the direction that the thumb points, that is the direction of n cap, that is certainly perpendicular to this plane, but in this occasion it shows that the thumb points into the screen. Using this right hand rule, we can always find the direction of this cross product. And then let us see whether what other rules are obeyed with cross product. I am writing A cross B plus C, this vector. It can be given as A cross B plus A cross C. That means distributive property is obeyed here. Also, B cross A equals minus of A cross B. The sign inverse, we can clearly see that from this picture. In this picture that we have drawn here, if we consider A cross B, we point the thumb into the plane. If we consider B cross A, then we rotate the fingers in this direction, and you can clearly see that the thumb points upward. That means the thumb comes out of the plane. So, this minus sign is well justified, and that means cross product is not commutative. And how can we interpret cross product? The interpretation for cross product would be the area of this parallelogram. That would be represented by a cross product. On the contrary, a dot product represents the projection of one vector scaled by the other. So, if we had a unit vector, one of these, say B was a unit vector, then A dot B would represent the projection of A onto B, that is this much of length, and that is a scalar. While cross product is a vector, it represents this area of this parallelogram with a direction that is perpendicular to this parallelogram. And depending on whether you are taking A cross B or B cross A, the direction would change. Okay. So, now let us consider Cartesian components in the vector algebra. So, in a Cartesian coordinate system, an arbitrary vector can be expanded in terms of basis vectors. So, let us look at it pictorially. Here I draw Cartesian axis, this is x, this is y, and this is z, and this is our vector A starting from the origin. Let us project this onto xy plane. That looks something like this, the projection, and this part of the length here can be given as Ax, that is parallel to x axis. This part is Ay, that is parallel to y axis, that is y component of the vector, and the z component would be its projection onto z axis. So, this is Az, and if we have unit vectors along x, y, z given as x cap, y cap and z cap, then this vector A can be represented as Ax, x cap, plus Ay, y cap, plus Az, z cap, where mathematically Ax can be written as A dot x cap. Here we see the interpretation, the projection interpretation of dot product clearly. Ay is similarly A dot y cap, and Az is A dot z cap.